all, my name is Richard Nugent. I'm an economist and the lead developer of the HEC FDA program at HEC. This series of videos serves as an introduction to the uncertainty around the stage damage relationship. In this video, we focus on the sources of uncertainty around the depth of flooding and the resulting percent damage. Let's take a more detailed look at what goes into the uncertainty around the damage to residential structures. There are two attributes about which we define uncertainty here. These two attributes are the elevation of the first floor and structure damage. Now, we care about the elevation of the first floor because we index depth percent damage curves to the elevation of the first floor. That's where the depth we say is 0, okay? And typically, the most consequential structure damage happens for flood depths above the first floor elevation. Now, why might we get the elevation of the first floor wrong? Could be due to survey errors or errors in topographic maps or layers, depending on the source of the elevation data. Structure damage is typically determined by a depth percent damage function unless entered directly. And why might we get this wrong? Could be due to errors in post-damage flood surveys or failure to account for critical factors other than depth, such as floodwater velocity, duration of flood, sediment load, building material, internal construction, structure condition, flood warning, salinity, among other things. The uncertainty around the damage that occurs to contents is closely linked to the uncertainty around the damage that occurs to the structure. The uncertainty around the elevation of the first floor still matters. And why might we not get content damage right? It could be due to errors in post-flood damage survey, failure to account for critical factors other than depth, and here we consider things like content location, floodwater velocity, duration of flood, sediment load, flood warning, etc. So as we see, for the first floor elevation plays a significant role in contributing toward the uncertainty around the damage that occurs at a given stage of flooding. The uncertainty is typically characterized based on the method of measurement and assigned based on the class of structure. For example, slab on grade versus raised foundation. The table on the right is Table 6-5 from Engineering Manual 1110-2-1619. The first floor elevation error and standard deviation of error calculated from the results in accuracy of computed water surface profiles, a 1986 study, are organized in the table. The standard deviation in the column on the right can be used to inform the standard deviation of error if using a method from this table. This work is due to be updated with newer and more accurate tools available to capture the first floor elevation. We should keep in mind that uncertainty in the first floor elevation has a bigger impact at lower stages. In the first video of this series, we looked at the stage damage plot and saw that the standard deviation of damages increases with increasing stage. However, the coefficient of variation, that is the standard deviation as a percent of the mean, which is a relative uncertainty measure, is actually decreasing as stage increases. And this, in part, reflects the lessening sensitivity of error to error in the first floor elevation as stage increases. In other words, when the depth of flooding is 10 feet above the first floor, whether the foundation height is 3 feet or 3.5 feet does not really change the fact that this structure has been totally inundated. When we look at a depth percent damage function, there are a number of factors that contribute to a range of possible levels of percent damage for a given depth of flooding, which are not explicitly specified in the depth percent damage function. Among these attributes, the hydrologic variables are very influential and have been organized along with their effects in the table on this slide. Velocity is a major factor that can aggravate structure and content damage. Velocity limits time for emergency floodproofing and evacuation, and the additional force from velocity creates greater danger of foundation collapse and forceful destructure of the contents within a structure. Duration may be the most significant factor in the destruction of building fabric. Continued saturation will cause wood to warp and rot, tile to buckle, and metal objects and mechanical equipment to rust. Sediment load can be particularly damaging to the workings of mechanical equipment and can create cleanup problems. And repeated saturations can have a cumulative effect on the deterioration of building fabric and the working of mechanical equipment. Now, these four hydrologic variables, they're not explicitly specified in the depth percent damage function, but as these things vary with depth, we're going to get a range of percent damage. There are a few sources for depth percent damage curves. Sources include the generic curves in the Economic Guidance Memoranda, such as Economic Guidance Memorandum 01-03 and Economic Guidance Memorandum 04-01, the FEMA HAZIS curves, and the depth percent damage curves developed in district offices. The key is to be able to specify a range of percent damage for a given depth and motivate why a given function applies for your study area. From Economic Guidance Memorandum 01-03, this is the generic depth percent damage function curve for a one-story residential structure with no basement. The range of percent damage for a given depth is plotted between the 95th and 5th percentiles under the assumption of a normal distribution. Observe that as the depth of flooding reaches the elevation of the first floor, that is depth of 0, percent damage is somewhere between 10% and less than 20%. And as the depth of flooding reaches 11 feet above the first floor elevation, percent damage is somewhere between 70 and 80%. From Economic Guidance Memorandum 01-03, this is the generic depth percent damage curve for content of a one-story residential structure with no basement. The same bounds are plotted with approximately 5 to 10% content damage for a depth of flooding at the first floor elevation, and approximately 35 but less than 45% content damage for 11 feet of flood depth above the first floor. Sources for commercial and industrial depth damage functions are more limited than as for residential. One option is the non-residential flood depth damage functions derived from expert elicitation, a 2013 IWR report. The large variety of commercial activities makes generalizations and therefore depth damage functions difficult. There is significant potential for large residual errors in the estimates, and content is highly variable. For large facilities, commercial and industrial risk-based stage damage curves may be entered directly, but this is usually done on an individual structure basis. You can ask a responsible person to provide a minimum, most likely and maximum damage to characterize a triangular distribution at each depth and carry out sensitivity analysis. Here is an example of aggregation of risk-based stage damage curves by damage category: residential, commercial, public, and total. Observe in this example, as expected, commercial has the greatest dispersion in damage for a given stage, and therefore is the largest contributor to the uncertainty in the stage aggregated total damage function. There are damage categories other than structure and content damage. These damage categories include agricultural damage, infrastructure damage, emergency and cleanup costs. And these other damage categories often are estimated outside HECFDA, although in some instances can be specified within the model. Other categories usually don't add too much in terms of benefits and can be difficult to estimate. How do we reconcile our requirement to characterize uncertainty with our requirement to be compliant with 3 by 3 by 3? We can use existing data, expertise, and experience to help reduce uncertainty. Each of these helps us to characterize the possible range of values for the parameters that feed into the stage damage function. The remaining uncertainty is addressed by making assumptions. Assumptions are significant and can have a big impact on the analysis. We must document all of our assumptions in the report. Reproducibility should be the standard of our work. Include justification and rationale for every assumption. Finally, risk-informed decision-making is more than just schedule and funding, but also a consideration of the risk of not selecting a reasonable plan, a plan that meets federal interest and is functional. If you have any questions, please feel free to email me, Richard Nugent, or post your questions to the Discourse discussion board. Thank you.